You are listening to Worth Electronics What's Up Radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We're going to be checking in with leading industry experts and our very own Worth Electronic technical specialists. We're going to shine a light on interesting topics such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with the Worth Electronics What's Up podcast. As we are all aware of, technology is advancing at a tremendous rate, and the next generation of devices are shifting towards wireless applications. The movement toward higher frequency into the gigahertz range has already begun, and more knowledge of components in these applications is desired. EMC continues to grow in importance, and there's now a demand to know the characteristics of EMC components used beyond their current typical application range. In this podcast, we're going to explain the different properties between multi-layer ferrite beads in high frequency and standard multi-layer ferrite beads, as well as a new methodology developed for the measurement of DC bias at higher frequencies. Lastly, we're going to talk about some uncommon applications where the higher frequency series are a suitable alternative to the more traditional design topologies that we usually see. Chip bead ferrites are one of the most used components for suppressing higher frequency noise in electronics industry. They're passive components with a high attenuation over a wide frequency range, and at the same time, they do not influence the useful component of the signal. They are commonly connected in series with the power supply or the signal source. Nevertheless, improper use of the ferrite bead in the system can degrade the overall EMI suppression capability. Ferrite beads can have different characteristics at different frequencies. These can be roughly separated into 3 different regions, including inductive, resistive, and capacitive characteristics. At its self-resonating frequency, also known as the SRF, the ferrite bead performs as a resistor, impeding high-frequency signals and then dissipating the power as heat. The intended use of ferrite beads for EMI applications is that the component must be in the resistive region over the frequency range, where the noise needs to be attenuated. Parasitic elements inside the bead drastically affect the performance as a function of frequency. In order to take into consideration these parasitic elements, the equivalent circuit is modeled in the following topology, consisting of an inductance, parallel capacitance, parallel resistance, and series resistance. This is frequently used in simulations to model a ferrite bead, and this model will be used to explain how these parasitic parameters influence the impedance curve. The Worth Electronic multi-layer ferrite bead family is categorized into different series. This depends on their intended application, the shape of the impedance curve, the core material, as well as the structure of the internal windings. Now, in response to the movement towards operating at higher frequencies, Worth Electronic has developed a new series called the CBF HF Surface Mount EMI Suppression Ferrite Beads, and the HF stands for high frequency. Here, a comparison between the standard series, which is the CBF, and the high frequency series, the CBF HF, will be explored. This series is specially fabricated to increase performance, which means higher impedance and lower parasitic capacitance at higher frequencies. A key factor in the electrical behavior of multi-layer ferrite beads at different frequencies is the construction direction of the windings and the internal design. The inner structure not only influences the frequency response, but also the impedance the chip beads can produce. Horizontal windings and vertical windings have a fundamental effect on the performance of ferrite beads, even within the same case size. To understand the performance, the formation of parasitics within the structure is analyzed. In order to understand just how the construction and parasitics influence the electrical properties, the association between this and the impedance of a chip bead is identified. The relationship to the overall impedance is described by applying the impedance equation. The main influence from parasitic elements comes from the reactive part of the equation. The lower the capacitive reactance and the more inductive reactance found in the total reactance, then the higher the magnitude of the impedance. The basic CBF design has horizontal windings layered in the vertical direction. This makes them easier to fabricate and it reduces production costs, but this type of structure yields a lower impedance with an impedance peak at a lower frequency than the WE CBF HF. The WE CBF HF has vertical windings layered in a horizontal direction. This horizontal structure is limited to the number of windings due to the structure height of a surface mount ferrite. On the other hand, the vertical structure utilizes the length dimension to increase the winding layers. In a horizontal winding, every winding runs between the connection terminals, creating a small parasitic capacitance between the winding and the terminal. Each winding creates layers of terminal, parasitic capacitance, winding, parasitic capacitance, terminal structure. These layers contribute to the parasitics as the subcircuits accumulate in parallel, creating a sum of capacitances that will decrease the overall reactance. In the ferrite bead, the WE CBF HF, the silver layer is formed like a wound air coil, and it loops steadily from one terminal to the other. This causes parasitic capacitance to be present between the loops as well as at each end terminations. So as the parasitic capacitance is in series with their neighbor, the overall capacitance is in the inverse of the sum of all inverse capacitances. Consequently, the total parasitic capacitance is just a fraction of the parasitic capacitance of that found in the ferrite bead WE CBF. This has the effect of increasing the SRF, and therefore the possible operating frequency range is shifted to higher frequencies. Consider for a moment the WE CBF compared to the CBF HF, which again is high frequency, where both are sizes 0603 of type wide band, and they have a peak of around 2.2 kiloohms. After the SRF, the ferrite bead becomes capacitive, and this effect of parasitic capacitances can be observed from their reactance behavior as the value is no longer rising, but instead it's falling. From the WE CBF, the parasitic capacitance becomes dominant at 100 megahertz, while the WE CBF HF dominates at 450 megahertz, shifting nearly 5 times higher in frequency than our standard part. Not only being able to have the SRF reach a higher frequency region, in this case, it also allows the use of a WE CBF HF over a wider frequency range than the standard CBF series. So for example, if we have a request for a filter with an impedance of 500 ohms, the WE CBF has a range from 30 megahertz to 300 megahertz, while the WE CBF HF has a larger range from 70 megahertz all the way up to 2,500 megahertz, permitting a much wider operation bandwidth. With the same size, type, and similar electrical characteristics, a wider usable bandwidth may mean less EMI issues in this particular region. This means the design of the inner structure windings contribute to the total parasitic capacitance. They sum up to be either in parallel or in series, and this can lead to achieving an SRF located in that higher frequency region. Furthermore, the bandwidth also shifts up in the frequency, and consequently, the range of use is higher and it may also be wider. So now let's talk about the effect of temperature and the DC bias current. The optimal selection of a multi-layer ferrite to suit the need of a specific application requires, among other parameters, actually defining the operational temperature and the DC current. External influences cause the multilayer ferrite to behave quite a bit differently. For example, a change of temperature can modify the magnetization state of a ferrite bead. In addition, the so-called DC bias effect is the current dependence of general ferrite materials. The DC current can also be correlated to the operating temperature of the component, as the part generates heat due to the current and therefore influences its electrical characteristics. Magnetic materials have a maximum useful operating temperature. At a certain point, the magnetic permeability of a material decreases strongly with increasing temperature. At temperatures where the thermal energy is greater than the energy supplied by the external magnetic field, the magnetic dipoles or elementary magnets become difficult to align, preventing the formation of a magnetic field. This critical temperature is called the Curie temperature. At temperatures above the Curie temperature, the ferrite loses its permeability and becomes paramagnetic or weakly magnetized. With this knowledge, the alignment can be destroyed by heating beyond the Curie temperature or through other methods of thermal exposure, shock, and even strong magnets. This effect is reversible. When the temperature cools below the Curie temperature, the ferrite regains its permeability and becomes ferromagnetic again. Using this sequence of events will allow the ferrite beads to be measured in a consistent manner by aligning the magnetic dipole to a remnant-free initial state. Ferrite beads are made to dissipate heat. However, the more it dissipates, the higher the operating temperature is reached. We can see a typical temperature profile of a chip bead with a Curie temperature above 180 degrees Celsius, and this is where the measurement is carried out from negative 55 degrees Celsius to 160 degrees Celsius. In our example, we can see that the higher the temperature of the component, the more the impedance is shifted down, becoming more saturated. The optimal operating temperature would be to stay as close to the ambient temperature, around 20 degrees Celsius to 25 degrees Celsius. Engineers should take this and environmental influences into consideration when designing those applications. Beside the temperature, multilayer ferrites are always operated under current bias. Therefore, measurements with DC bias give essential information about the component's behavior during the operation. The impedance profile is graphed to depict the influence of various DC bias current conditions. As the applied current increases, the internal core material moves towards saturation, causing a drop in inductance. This saturation is due to the maximum magnetic dipole alignment, and this will change the permeability, hence impedance, of the ferrite. Now, as shown in the low-frequency region, the biasing current has a more drastic effect compared to the high-frequency region. As the DC bias current increases, the inductance decreases. However, the parasitic capacitance always stays the same. This leads to the SRF peak to shift right towards higher frequencies. In addition, the damping resistance also becomes lower and it moves right, causing the quality factor to increase. In this scenario, surface mount ferrites produce sharper and higher SRF peaks. Lastly, it can be seen that the impedance converges towards one point of the end of this frequency range, which for the WeCBF HF is at 8 gigahertz. This is caused by the ferromagnetic effect dominating up to the SRF. Above the SRF, the ferromagnetic effect is still present. However, it's hidden by the resonance and capacitive effects. The ferromagnetic properties lose their influence with decreasing permeability and become paramagnetic. But in this state, the bead physically acts like a wire coil at its capacitive state due to parasitic capacitance. The amount of magnetic field strength which causes saturation actually differs depending on the material used for its core. For example, nickel zinc is a commonly used core material and it displays ferromagnetic properties. So in our attached figure 1, we see two CBF high-frequency parts that have similar properties but different core material. Both parts are defined in the datasheet at 100 megahertz with a typical impedance of 600 ohms at 0 amps DC bias current. As the components each have different saturation levels, when the ferrite beads are exposed to a DC bias current of 100 milliamps, both parts saturate and impedance decreases rapidly. However, one of our components, seen in the orange curve, actually has a higher saturation level, and it can maintain its impedance levels compared to a decrease in impedance from the blue curve. At 100 megahertz frequency marker, a clear drop in value is seen after 100 milliamps bias current is applied. Depending on the material, there are different responses to saturation current. Influence from temperature and DC bias are key parameters for the selection of the correct component. The impedance graphs of chip bead ferrites can be found in the respective data sheets with a DC bias current graph showing key current values. However, Worth Electronics' measurement-based online design platform RedExpert can be used to easily determine the impedance as well as other electrical characteristics of any chip bead ferrite at any operating frequency and DC bias current. Alternatively, incorporating a chip bead ferrite into a simulated design for evaluation is possible with the availability of S parameters and SPICE simulation models. The common industrial impedance analyzers and DC bias test fixtures for surface mount devices have reached their frequency measurement limitations. At frequencies above 1 gigahertz, measurements are inherently unstable or not possible due to the measuring method. So in addition, an external supply of up to 5 amps is the maximum applicable DC biasing current available. This limits the information provided in datasheets for those designers who want to know the profile of a multi-layer ferrite bead. In light of this, Worth Electronic has developed a new and enhanced measurement technique for these surface mount components. With this patented technique, it's possible to measure impedances for frequencies higher than 3 gigahertz with DC bias currents up to 20 amps. In order to achieve frequencies beyond 3 gigahertz, an impedance analyzer is no longer sufficient, and a vector network analyzer, or VNA, becomes more advantageous. This allows more information to be provided in ferrite bead datasheets and not to be restricted from the measurement setup. The impedance analyzer DC bias test fixture utilizes a push and hold action on the ferrite bead onto gold electrode contact pads to measure the values. However, this setup actually has low repeatability as the connections with the termination is not fixed. In contrast, the new design minimizes this error completely by providing a solid connection, where the device under test is soldered down and tested on a PCB. In a real-world application, ferrite beads are used soldered onto a PCB. Therefore, this measurement method provides a more realistic and equivalent test environment. In addition to keep measurement consistency, the components are put through the reflow oven past the Curie temperature of the material to solder the parts onto a PCB. Correlating to the influence of temperature, this forces the elementary magnets to align to a remnant initial free state before the start of a measurement. To prove the measurement data up to that 3 gigahertz range can be replicated with the new measurement setup, the CBF HF series was measured and also compared. The results of the CBF HF using an impedance analyzer up to 3 gigahertz and VNA up to 8 gigahertz are nearly identical. This confirms the validity of the results from the new patented technique. In our attached figure 2 of this podcast, we see the block diagram depicting the design of the new test fixture and measurement setup with test circuit design. Here, the VNA and the power supply are remotely controlled to collect the measured data and adjust the DC current. The internal DC bias power available with conventional measurement instruments is limited to a few amperes. Consequently, it's unable to provide currents of more than 5 amps. The new jig allows an external power supply to be connected, where the limits are bound by the maximum current of the power supply device and the heating limit of the PCB. This measurement methodology allows valuable information in the high-frequency region and high DC bias applications to be provided for better understanding of the component's performance. A major difference of this setup is being able to consider the environmental settings and procedures. Before obtaining the electrical properties close to reality environment of the DUT, like soldering the part onto a PCB, is now included in the process leading up to the measurement. Many EMC problems from electronic devices can actually be solved using a chip bead ferrite solution in the EMI signal path. Numerous IoT applications now have wireless integrated into the devices, and Worth Electronic provides multi-layer chip bead ferrites to ensure that no EMI problems are generated. There are many applications where a ferrite bead are commonly used, such as suppression on signal lines, high-frequency RF modules, filtering harmonics for mobile communication, data line filtering in high-speed bus systems, filtering circuits, impedance matching circuits, and DC biasing. However, it's interesting to show different perspectives of using a chip bead in different application scenarios. So here are the more uncommon applications where the high-frequency chip bead ferrite is a suitable alternative to components that are traditionally in these circuit designs. First, the broadband amplifier. Broadband amplifiers are often needed in receiving applications when using antennas to reproduce a wide range of signals with low noise. The bias network is one of the critical aspects in RF circuit design. It determines the amplifier performance over temperature as well as DC bias conditions. The DC voltages applied in an amplifier cannot be applied directly. Therefore, a high impedance component is used to ensure the complete RF signal passes through the device and not back through the DC bias circuit. The current bias is seen as a high impedance element to the RF signal, allowing most of the information to pass through the device, therefore supplying a stable current to the output. A standard inductor does not operate over a wide frequency range, having a smaller resistive area profile, roughly in the range of 200 MHz to 2 GHz only. For a standard wire-wound ferrite, the parasitics begin to dominate, resulting in capacitance and less inductance. An alternative to provide wide bandwidth for broadband use is to substitute the air coil inductor with the WE CBF HF ferrite beads. High impedances in the power supply path above 200 ohms can drive the gain block, and additionally, for impedances lower than 200 ohms, the RF signal at the output of the gain block will be attenuated. The advantages of using a WE CBF HF include a wide band of frequencies, stable inductance, and RF signal passes through to the output. Another application is the anti-aliasing filter for analog to digital converter, also known as ADC. It's usually necessary to place an anti-aliasing filter before an ADC to attenuate the unwanted higher frequency noise and signals. The common LC formation of a low-pass filter, or LPF, may have effects of underdamping, which creates a resonant peak at a frequency band around the switching frequency of the converter, consequently results in the amplification and unwanted switching noises. Using a filter bead in series with the inductor will dampen and smooth out the LPF response, and additionally act as an impedance transformer. The standard way to design a filter for an ADC includes RC and LC topologies with or without using operational amplifiers, also known as op-amps. As a first-order filter, an RC filter produces a fall of -3 decibels at its cutoff and a steepness slope of 20 decibels per decade step-down frequency response. This is generally not enough to provide a strong filtering system. An LC filter usually has low resistivity and high inductivity. As a result, minimal damping creates unwanted oscillation. Since an ADC does not have a standard resistive load, when a peak load occurs, the measure of this load can be identified as a resonating peak at the corner frequency. Instead of attenuating noise, the resonance peak is a reason that causes the noise to amplify. Resistor and ferrite beads can be used to damp a system to reduce the amount of resonant peaking. Since a ferrite bead still has a high Q factor, it actually acts as an inductor in the low frequency region. The resistive part of a ferrite bead does not become dominant until reaching the megahertz range. Therefore, in general, the WE CBF-HF has higher inductance compared to the WE CBF, even in low frequency regions. Due to their construction, a low cutoff frequency is achievable. The advantages of using an additional chip bead ferrite here include 40 decibel per decade ramp down frequency response, suppression of the resonance peaking, taking less space and fewer components than an op-amp circuit design, and it has an overall filter design at a lower cost. Our third and final application example is terminating for long periodic dipole antenna, also known as LPDA. LPDA are now used in many applications operating over a wide band of frequencies. LPDA consists of a number of dipole elements gradually increasing in length, where the elements are spaced at intervals following a logarithmic function of the frequency. Printed LPDA layout is an alternative way of applying this antenna array using microstrip printed technology. Designing an antenna on a PCB has different considerations to take into account. For example, not only an accurate calculation of the length and distances of the element, but the compatibility of the microstrip line tracks to the PCB is just as important. In the design phase, there may also be PCB size or material budget constraints. When a higher front-to-back ratio at the lowest frequency is desired, the antenna feeder should include a high impedance termination stub. This shorted stub acts as a reflector to ensure a match is provided to the antenna feeder. This length is a quarter of the longest element. Therefore, depending on the operating frequency and size, a suitable length is calculated. Conventionally, the length of the antenna is used to transform the system to the frequency range to terminate, such as a quarter wave impedance transformer, since the length works at a specific narrow-banded frequency. An alternative is actually to use a real component that also has high impedance in the frequency range. An antenna with stub traditionally starts at the stub, and the cutoff is far from the stub. Similarly, an antenna with high impedance and high frequency chip bead operates before the stub and also has a cutoff far from the stub. In contrast, a ferrite bead with not enough impedance will cut off earlier near the stub, shortening the usable bandwidth. The high-frequency chip ferrite fulfills the requirements with its high impedance peak, ranging from 100 MHz to 1 GHz. By using a ferrite bead, not only is the same size PCB kept by saving the space that would be occupied by the line transformer, the operative frequency range is also widened. Advantages of using the WE CBF-HF include a wider operating frequency, smaller PCB size, and lower cost. In summary, the WE CBF-HF is a component suitable for suppressing EMI at the higher frequencies commonly found in new and existing device technologies. The WE CBF is still the component of choice when operating at lower frequencies. Additionally, a new developed measurement technique for surface mount components providing an insight of its frequency behavior up to 8 gigahertz and applicable current up to 20 amps. Lastly, due to the unique features of the WE CBF HF, it can be used in a range of applications that are not typically associated with chip bead ferrites. Implementing the WE CBF and the WE CBF HF in your design has never been easier with S parameters and SPICE models available through Worth Electronic Online. With the inclusion of the WE CBF range, circuit designers now have even more flexibility in their ferrite bead selection, ensuring the right component is found for each application. Attached images are available in most podcast streaming networks. To view all images, visit www.we-online.com/podcast. To download the complete application note discussed today, visit Worth Electronic Online at www.we-online.com/appnotes. You're listening to Worth Electronics What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and our very own Worth Electronic tech specialists. We're going to shine a light on interesting topics such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up podcast.